Hi, this is Michael of MCM Design. You're looking at my Astrocade, formerly known as the Bally home computer, which I modified back in the 1980s to run in the low and high resolution modes. Part 1 of this 5-part video series is my video proof that this computer runs perfect, both in the low and high resolution modes. In this Part 4 video, I'm going to disassemble this computer so you can get a close look at its hardware. This computer has a TTL input interface for this 54-key matrix keyboard, which I purchased back in the 1980s from Jamco Electronics. A wide 24-pin DIP ribbon cable connector plugs into the keyboard. The other end of the cable feeds into the back of the computer and plugs into an internal socket. I also cut down a cassette connector assembly so I could use a remote 24-button keypad at table height on the left side of the computer, since I am left-handed. The keypad connects using a small 14-pin DIP ribbon cable which plugs into a socket mounted on the bottom left console. This remote keypad connects to the rear wiring of the internal keypad. The custom cover on the top of the computer was a gift from Alan Schweitzer for troubleshooting some of his Astrocade motherboards. Thanks, Alan. This is a cool looking cover. Here are the two cables that plug into the keyboard, the keypad. The keyboard has a socket here that the cable plugs into. The keypad has a 14-pin wire wrap socket. Using number 30 wrapping wire, I wire the end of the keypad to that socket. I purchased a Viper cabinet back in the 1980s to house all of the add-under hardware. This cabinet does not utilize any of the Viper hardware sold in the 1980s. I installed a power-on LED in the front of the Viper cabinet. I am now going to remove the Viper side panels so I can swing the Astrocade up and back, allowing access to the hardware in the Viper cabinet. The Astrocade is hinged onto the back of the Viper cabinet, so it can easily be swung up and back to access the Viper interior. Let's take a close look at the Viper front interior. At the upper left is the black Bally power transformer. I actually removed the transformer from its plastic case. The plastic case is mounted to the Viper bottom. There is a custom 120 volt AC receptacle inside the case, and so the transformer plugs into the top of this case. This setup allows the heat generated within the transformer to dissipate easier. The transformer primary winding is fused to help protect it from a short or near short on the secondary side of the transformer. You can see the white fuse holder with red wires on the right. There is an AGC 1/2 amp fast blow fuse in this holder. Just to the right of the Bally transformer, you can see a pair of green and red wires for the power-on LED mounted on the Viper front. In the center is a Radio Shack triple power supply board that outputs plus 5 volts, plus 12 volts, and minus 5 volts. To the right of the board is the 120 volt AC step-down transformer used for the Radio Shack board. The Viper cabinet has a built-in forced air fan pointed up towards the Astrocade to move air across the top of the Astrocade motherboard to help dissipate heat generated by the custom address and data chips and certain power supply components. There are cutouts at the bottom of the Astrocade and top of the Viper cabinet, which allow the forced air to enter the Astrocade. The left and right sides of the Viper cabinet have ventilation openings with covers to help draw air into the Astrocade. Even with the poor ventilation in the Astrocade console, the forced air fan keeps the heated Astrocade components surprisingly cool. Now let's take a close look at the rear interior of the Viper cabinet. As mentioned previously, the Astrocade is hinged to the Viper cabinet to facilitate easy access to the Viper interior. As you can see, the Astrocade swings pretty easy. At the back left is a 120 volt AC receptacle for plugging in a cassette tape player recorder. Receptacle is right here. To the right of that is the main power on-off rocker switch, located down here. Above this switch is the main inline fuse holder, right here. And finally, to the very right is a RS-232C board provision. Here's the board right here. This board is wired to a Z80 dart scheme provision, which is up here. There are two type DB25 connectors, not visible from here, that are mounted below the RS-232C board and are accessible at the rear of the Viper cabinet. The Z80 Dual asynchronous receiver transceiver was originally intended for use with my Epson LQ-850 letter quality dot matrix printer. There is room below the 50-pin expansion cable. Here's the cable, and you got lots of room underneath here. There's room here to insert a second expansion cable for a remote hardware board, which for me would typically be the Balchik HR board to run troubleshooting diagnostic programs or graphic demos. The second 50-pin cable would be connected right here, just above the first cable connection. Now it's time to take a look at the significant intent of the Viper cabinet to house the screen RAM, user RAM, high-res ROM, keyboard interface, and Z80 dart scheme. You are now looking at the add-under chipboard. If this is the first time you've seen this board, you might react saying, "Man, there's sure a lot of chips on this board." I certainly would agree with you. The high-res screen RAM alone requires 32 chips. Let's take a closer look at the screen RAM area now. You're looking at the screen RAM area of the add-under chipboard. There are 32 chips used just for screen RAM alone. These 32 chips are grouped into 4 banks of 8 chips each. The 4 banks are designated as Bank 0, Bank 1, Bank 2, and Bank 3. This is Bank 0, Bank 1, Bank 2, and Bank 3. Bank 0 is used for the low resolution mode, which maps 160 by 102 pixels to the TV screen. This requires 4 kilobytes, that is 4096 bytes of RAM memory. The custom address and data chips were designed to interface to dynamic RAM chips having a 16-pin package. This particular DRAM chip requires 3 power supplies, in this case plus 5 volt, plus 12 volt, and minus 5 volt supplies. Each chip stores a specific data bit. The data bit has a specific label. The specific data bit for each chip is labeled like this: D0, D1, D2, 3, 4, 5, D6, and finally D7. In high res, this same labeling is repeated for banks 1, 2, and 3. Each bank has 8 chips, so only 8 bits, that is 1 byte of screen RAM, can be accessed at one time. It takes 2 bits to define a pixel. With 2 bits, the binary possibilities are 00, 01, 10, and 11. This is why one pixel can be displayed in only one of 4 possible colors. The high-res mode requires 16 KB of screen RAM, utilizing all 4 banks 0, 1, 2, and 3. By adding a few more logic gates, it's actually possible to map a medium resolution of 160 by 204 pixels to the TV screen. MCM Design plans to investigate and test Perkins Engineering's medium resolution map, which could possibly be included in MCM's final high-res Astrocade project. Additional chips are required for the screen RAM scheme. There's the address line buffer chip right here, the data line buffer chip here, 4 type 74-253 chips here, and finally 4 74 LS166 chips, which are used only in the high-res mode for scanning the TV video display. Now let's take a look at the screen RAM timing and control chips. In this video clip, there are a dozen chips utilized for screen RAM to generate specific clocks, RAM control lines, and high-res video scan timing. There are also several chips and logic gates used to provide a software select for the low and high-res modes. A 24-pin DIP ribbon cable connection taps appropriate signal lines from the motherboard, which has been modified to provide those signal lines to a 24-pin socket mounted on the bottom of the motherboard. The 24-pin DIP ribbon cable connection is located right here. 4 additional lines are provided using the 50-pin expansion ribbon cable. The 50-pin expansion cable is located right here. You are now looking at the area of the add-under board, which provides user RAM and ROM. One 32 KB static RAM chip is addressed from 8000 to FFFF hex. That's this chip right here. A second 32 KB static RAM chip is addressed from 6000 to 7FFF hex. That chip there. Its socket is multi-carded using 2 dip switches, providing 4 8 KB banks, which can be switched using a mini toggle to the cassette ROM address from 2000 to 3FFF hex. Both user RAM sockets are compatible with a 32 KB type 28256 EEPROM. There is another mini toggle switch to write protect user RAM. Both mini toggle switches are accessible at the rear of the Viper cabinet. There is also a socket provision for an 8 KB EEPROM addressed from 0 to 1 FFF hex. This provision is intended to substitute an 8 KB high-res BIOS for the standard 8 KB low-res BIOS on the Astrocade motherboard. Several chips are required to decode this user RAM high-res ROM scheme. A specialty 8-pin 75451 chip deals with the motherboard buzz-off line. So a remote hardware board like the Bally HR board can be connected to this high-res Astrocade using a second 50-pin expansion connection. You can partially see the second 50-pin connector right here. Also viewable to the right is the C80 dart provision and 54-key matrix keyboard interface. Let's take a quick look at the bottom side of this under a chipboard. This video clip was included for Astrocade enthusiasts curious about the underside of a wire-wrapped RAM board that has 50+ chips on it. It is helpful to use multicolors of number 30 wrapping wire. You can see the two mini toggle switches mounted on this board at the upper left. 0.1 microfarad decoupling, also referred to as bypass capacitors, can be soldered on the bottom of the wire wrap sockets on the very end of the wrapping posts. I chose to use disc capacitors. Ceramic caps would probably work just as well. I used the Moztec 1980 Memory Data Book and Designer's Guide, pages X-34 and X-35, as a guide for decoupling the 4 banks of dynamic RAM, and I also referred to the Datamax UV-1R screen RAM board components layout. I built a custom audio-video wire wrap board that replaces the Aztec RF modulator. This custom board has a motherboard 9-pin quick connect. I found a scheme that utilizes the LM1889N TV video chip without any RF components. This chip's output is fed into a composite video driver which uses a 2-transistor configuration. It's the same driver used in the Datamax UV-1R computer. There is also a type LM377 audio stereo amplifier. One channel is used as a TV audio driver. The other channel will drive a remote 8-ohm home speaker. There is a standard headphone jack and volume control for a remote speaker. A long time ago, I plugged a home speaker with an 8-inch woofer and I think a 3-inch tweeter into this board. This speaker was bigger than a tabletop or bookshelf speaker. Wow, what a difference compared to a TV speaker. The custom input-output chip really outputs a smooth bass response. There is a quick connect for a plus 5 volt and 12 volt connection. Here's the quick connect for the motherboard, the LM1889 chip, a NTA substitution for a LM377, and the ground wire. And here's the standard headphone jack, the RCA type video output jack, and a mini volume control. And there's 2 small number 30 wires for connection to the audio jack that's mounted on the motherboard lower console. And as you can see, this board has been hardwired with number 30 wrapping wire. This is the top view of the modified for high-res motherboard that is used for my high-res DRAM Dynamic RAM Astrocade. Here's a brief tour of this modified motherboard. There will be a real thorough look at a modified for high-res motherboard in my next video series. The most obvious is the missing 8 DRAM chips and U23. 8 DRAM chips here and U23. I chose to remove all the RAM's decoupling caps and 6 1K ohm address line pull-up resistors. These caps and pull-up resistors were all in this area. They're now gone. I chose to remove the unnecessary chips U21 and U22. U22s are now missing. The power resistor R1 was moved to the left so a 24-pin wire wrap ribbon cable socket could be mounted on the motherboard bottom. Here's the power resistor R1. It used to be over here. Now you can see 2 screws fastening that 24-pin socket to the bottom of the motherboard. You might be able to see 6 blue wrapping wires connected from the ribbon socket to the 6 RAM address lines A0 to A5. They're pretty thin, they're hard to see. You might be able to see them. There's 6 wires connected from the socket to the motherboard. I replaced 5 power supply electrolytic caps with new caps. 2 new caps here, one here, one down here, and one here in the corner. I removed all the RF shielding around the 2 7 MHz clocks. This board uses one of those kludge boards. It's possible, if you know what you're doing, to remove all the shielding in this area. I'll probably show that how to do that in my next video series. You can tap -5 volts off the motherboard since 4 high-res RAM banks draw only a few milliamps. Here's the yellow -5 volt wire that you can tap off the motherboard and connect it to the add under RAM board. I also hardwired a black ground wire to connect to the add under DRAM board. You can barely see the black wire here for connection as a ground. And finally, you can see a portion of the wiring for the socket mounted on the console bottom for the remote keypad. Here's the wiring to the remote keypad. You can barely see it. The wiring is connected to the very end of the motherboard keypad mounted at the motherboard. This is the bottom view of the modified for high-res motherboard. This clip shows a rewire of one end of the power resistor R1 that was moved, along with the 18 wire taps from the motherboard to the 24-pin ribbon cable socket mounted on the motherboard bottom. There is a double-wrapped blue wire from R1 to the voltage regulator VR2 input. Here's the connection right here. Here are the 18 taps. 2 red wires to the custom data chip serial 0 and serial 1 at pins 11 and 12 respectively. Pins 11 and 12 must be removed from ground. Here's the connection here. 1 white wire to the U23 pin 1, which is the data enable line. Here's the white wire connection here. 8 yellow wires to the custom data chip lines MD0 to MD7. The lines tapped at the 8 RAM data input pattern 2. All 8 wires are soldered to the RAM pattern pin 2. 4 red wires to the 4 RAS0, the RAS3 lines at the custom address pins 9 and 11. Here are the 4 connections here. 1 green wire for the PX clock at U20 pin 9. Connection is up here, the green wire. one yellow wire for the inverted 7 MHz clock at U6 pin 6. Connection here, U6 pin 6. And finally, one white wire to the inverted 1.78 MHz system clock at the end of the 150 ohm resistor R18. This is the end opposite to the resistor end connected to a U15 pin 13. Here's the connection here. Note it is not connected to U15 pin 13. Again, that's a total of 18 wires tapped at the bottom of the motherboard. That concludes this Part 4 high-res DRAM Astrocade disassembly.